Yeah, I had the mic. And then I'll pass it on to you. OK, so let's get started. My name is SVN Vishwanathan, and I'm one of the lead organizers of this school. And on behalf of Purdue University, the Department of Statistics, the Department of Computer Science, and the Machine Learning group in general, I'd like to invite you to this edition of the Machine Learning Summer School at Purdue University. This school has been made possible by generous contributions from a number of different people, both in terms of money and in kind. In particular, I'd like to thank NSF for providing us money to give out student scholarships. We also received generous funding from a number of industry participants, such as Yahoo, Microsoft Research, and IBM. And I'd also like to acknowledge the contribution of hundreds of hours of work that have gone into putting together the program and making the school possible, because from the various organizers that helped organize the school with me. In particular, I'd like to thank Sergey Kirchner, who is one of the lead co-organizers, for putting in hundreds of thousands of hours of work in this. And also all the student volunteers who are responsible for various facets of the school. And so far, if the reason the school is running smoothly, it's mainly I credit these people for all the arrangements so far. And last but not the least, I'd like to thank all the participants for participating in this school. And welcome to Purdue, and welcome to the Machine Learning Summer School. Thank you very much. So now I'd like to introduce Bob Skill. He's assistant head of the computer science department. He's a professor of computer science and a professor of mathematics, and he'd like to say a few words to welcome us all. There you go.
On behalf of the computer science department, I would like to welcome you to the Machine Learning Summer School. The department is pleased to be co-hosting this event. 4 of our members, Professors Chris Clifton, Lo C, Jennifer Neville, and Vichy, are involved in organizing and in lecturing at this summer school. We have an active and energetic machine learning group in our department. We are proud of their research achievements and their contributions to our teaching mission. Concerning machine learning, it is well known that machine learning plays an important role in constructing software having characteristics that we associate with intelligence. Speaking of IBM, IBM's Watson demonstrated this to a remarkable degree. It is no doubt that in the foreseeable future, machine learning will be a hot area for both research and development. My remarks are brief, and so I'd like to close by wishing you a stimulating experience in the summer school, and hope you enjoy your 2 weeks here in the Purdue campus and the West Lafayette community. Thank you.
All right, can you hear me all right? It's recording, good. All right, I'm Sergey Kirchner. As Vishy alluded, I'm also one of the co-organizers of this event. It's actually my pleasure to introduce our first speaker to you. It's Professor Dale Schuurmans of University of Alberta. Dale, would you mind standing up? Dale's research interests are in machine learning, artificial intelligence, statistics, and optimization. He's made a number of original contributions to all of these areas. He co-authors over 100 papers. And I guess more importantly, he co-supervised 20 PhD students. In fact, I did a postdoc at the University of Alberta, and I remember at that time Dale had 9 students at the same time. So we barely saw him, but his students did. He served in editorial boards of IEEE PAMI Journal, Artificial Intelligence Journal, Journal of Machine Learning Research, Machine Learning Journal, Journal of Artificial Intelligence Research. And he was a program co-chair for NIPS in 2008, and he was the general chair of NIPS 2009. and he served on many other program committees and other conferences. He received many outstanding paper awards at many prestigious conferences. Let me add one more thing. He did not want to put it on his bio. Dale is a Canada Research Chair at Tier 2 at the University of Alberta. And Canada Research Chair, you can think of it, it's kind of like a distinguished professor. So without saying much more than that, Dale Schuurmans.
Is this loud enough to pick up on the mic? Perfect? Yeah, OK. It's a trick. It's just for the recording, I suppose. All right, well, it's a real pleasure to be able to join you here this morning. I confess that I'm from a different time zone, so this is incredibly early for me. So I planned to start early. In fact, I'd volunteered myself to give the first lecture, which by default really means somebody has to introduce machine learning, at least ease you into some of the issues that likely are going to be investigated through the week. So I thought I'd start out pretty simple and try to ramp up and see if I can calibrate as we go. So machine learning. Now, machine learning is actually a big field, especially if you consider learning itself. And it turns out that learning phenomena are varied. It's not like one simple phenomenon that we're interested in the world. If you look in the sort of natural world at learning phenomena, you see a whole array of diverse things that really are considered learning. Things like reading and instruction, gaining knowledge, discovering patterns, actually experimenting and understanding causal relationships between mechanisms, or even practicing or motor control or skill acquisition, all the way down to growing and maturing or evolutionary processes. These are all instances of natural phenomenon that we would call learning. Interestingly, though, although they're all of interest, if you really look at the research literature and a lot of the current activity, it is not uniformly distributed through all these phenomena. In fact, it's heavily concentrated on a few key areas. I'm not saying that's a good thing. In fact, it probably isn't. It's a good idea to maintain some awareness of other phenomena around things we might be interested in. So machine learning in particular, of course, is about computational approaches to these phenomena. So we could think of it generally as just computational methods for capturing natural learning phenomena on computers. More operationally, we would think of this as just computer systems that improve with experience. Now, there's a central question, of course, in machine learning, which is how to improve with experience quickly. We're not interested in learning mechanisms that take till the heat death of the universe to get anywhere, right? If you really pose the question, like, how can you acquire meaningful capabilities quickly, you quickly run into hard limits. That is, there is no magic answer here, right? There are actual fundamental limits to what learning can do. And in fact, learning, especially when we try to operationalize it and solve problems, is about a fundamental trade-off between prior knowledge and constraint and the data that's available. Just to make a simple point, what's the best possible learning algorithm you could have? It's to have the answer in the first place, then you don't need any data. Okay? What's the second best learning algorithm you could have is to basically have decomposed all the possibilities into a partition where a single observation or a single experiment tells you exactly what the right answer is, right? One-shot learning. Now, clearly, these mathematical limits aren't going to go away, right? So the game is going to be about understanding the nature of these limits and how we can manipulate them to our advantage. Now, naively, I can't resist, but naively when people start thinking about machine learning, especially when I did, is I got all excited about thinking about artificial intelligence and capturing human learning phenomenon in a computer. The thing that naively people sort of forget to think about if they think like, oh, human beings are universal learning algorithms, or maybe the humanity is a universal learning algorithm, is that human beings as individuals are actually not universal learning algorithms, right? They are heavily constrained in their perception, in their learning, and their cognition. And in fact, understanding the nature of these constraints itself is a major scientific enterprise, right? So I just want to just kind of have fun for a minute to try to convince people that you bring many prior constraints to your perception and cognition that for the most part you are not aware of. So just briefly, to dispel this notion of universal learning, let me just test your perceptual capabilities, okay? So understanding the nature of human perception and learning is not like just declaring Kolmogorov complexity and declaring victory, right? There's a lot of detailed structure there. So for example, you look at a black and white image. Can you tell what that image is? Yeah?
It's like a dog, but upside down.
Yeah, it's upside down. Can you see it now? How many people can't see the dog? Yeah, okay. So if you, there's the head, there's the body. It's a Dalmatian. How many people still can't see the dog? Okay. Now, you might have noticed that, those of you who couldn't see it right away, right, you can't see, it just looks like a bunch of random blobs. And then suddenly some coherence emerges, and that coherence rapidly spreads through the whole scene. And suddenly you see more than just a dog, you see sort of a sidewalk, you see trees, you see leaves, right? And yet you have no sort of conscious awareness of how it is that you see, how it is that you put together all these pieces from nothingness to coherence, okay? This is not an exercise in just information compression. There is a lot of structure that you impose on scenes like this to uncover coherence. If you don't believe me, here's another just cute demo. Human beings, in fact primates, have a preference for lighting conditions at a certain angle. In particular, we have a preference for lighting conditions to the upper left. What you might imagine, you're holding things in your right hand predominantly. Lighting from the upper left would be sort of a favored lighting condition. So you look at a field of objects. So here's an object, it's a square lit from the top left, I believe, right? If you look at a field of objects like this, okay, watch the following. Can you find the one that pops out? Boom, okay? One of those blocks is upside down, you see it instantly. Well, that block was lit from the bottom right, okay? What happens if they're all lit from the bottom right and one of them's lit from the top left? It's not the same thing, right? You actually search. Try again. This is a little harder. The lighting conditions are a little less extreme. Boom, right? Lit from the bottom. This is really hard. I'm kind of cheating a bit with the shading, but there's this guy here. Okay. So, that's not machine learning. That's just perception. But there's all of these built-in biases and constraints in the way you apprehend the world, okay? You're not aware of them. So imagine if you sit down at a computer and you're trying to code computational systems to mimic or replicate these capabilities. We don't really know how to start, short of doing a lot of heavy investigation. So it's been an arduous journey to really uncover, say, human-level learning. Just the last sort of quick demo. Many of you would know this, but even our sort of cognitive structures, the way we understand language, is largely unavailable to our conscious awareness. So I present a sentence to you like, time flies like an arrow, okay? And for 90-some% of you, your first reaction is you only perceive one meaning for that sentence, right? Some metaphor about time going by quickly, right? That sentence has at least 7 coherent meanings, right? In the right context, if you're reading any one of those 7 meanings, you would reach, and you would reach without being consciously aware of any of the other 6 meanings, okay? Some of you probably know this already, but can someone help me out? Do you know another meaning for this other than just the metaphor of time going by quickly? There's 6 others, believe it or not.
You should time the speed in which flies.
That's right.
Like your time and arrow.
So in fact, there's a command. I want you to go out there and time those flies the same way you would time an arrow. There's actually 2 other commands, okay? I want you to go out there and time those flies the same way an arrow would time those flies, okay? There's a 3rd one. I want you to go out there and time those flies, but not just any flies, the ones that are like an arrow, okay? Okay, there's another class of meanings. Yeah?
Time flies, enjoy arrows.
Yes. So there's this peculiar species of flies, time flies, and they happen to like arrows. There's 2 versions of this. It turns out that the time flies all like one single magical arrow, or each time fly has their own little special arrow, right? Time flies like an arrow. The last one is kind of lame, but there's actually a completely distinct meaning from those. It's hard to get. Well, it's kind of a cheat. It's time as in Time magazine, an object. And so Time magazine flies like an arrow, Newsweek flies like a balloon, all right? Now, any one of these meanings, some of them fanciful, but you read fiction, As you read, you interpret and you understand what's being said. And when you're interpreting and understand what's being said, you're not sitting there looking at a list of 7 meanings and consciously aware of how you're matching them up and making a selection, right? All of this is happening below the surface. And it is not happening by just data compression. There is a lot of structure and principle going on there, all right? Anyway, so the first thing I want to dispel is this kind of naive intuition that there might be something like, one answer, a universal learning algorithm. It's like human learning. It goes out there and does everything for us. It's not going to happen. And if anything like that does happen, it's heavy structured engineering of human perceptual cognitive capabilities, which takes lifetimes of research to make progress on. Okay, probably when you think of an introduction to machine learning, you're probably thinking of something more mundane like this, which is, well, the reason we're all interested in machine learning is, gee whiz, there's all this data now, right? All data now is being captured electronically. More of it's being captured. It's comprehensive. It's being stored. And of course, computation itself, communication, computation, storage is all very cheap. So it's no surprise that automated analysis of all this data is of growing industrial and commercial importance and social importance. Okay, just sort of a specialization of this point is that machine learning you could look at as an effective development methodology. Instead of taking a problem like, ooh, how do I write a natural language understanding system, or like how do I write a web retrieval system or a document processing system? We might normally think of a standard engineering methodology as sitting down and thinking hard about the problem and writing the program, right? We take inputs, we produce outputs, okay? One of the characteristics of these domains that machine learning is having an impact in is that human beings are not capable of sitting down and actually understanding what the input-output map should be, right? However, at the same time, there's data. So you could look at machine learning as a particular type of system engineering methodology where we tackle problems where we as human beings don't know a priori what the map should look like, but we have access to enough data that we can essentially let the data determine the program, right? Just let data set parameters or set structural parameters of the program. And this is, largely responsible for the growing interest in this field. And as you know, it's having a huge impact. So I'm not going to go through this laundry list, but it's quite impressive, the numbers of applications that are becoming more and more effective and more deployed in the world, where essentially learned processing algorithms are now doing things like complex data interpretation tasks in many different applications for us. And in some cases, not just interpreting data, but executing actions based on that data. All right, that's my introduction to machine learning. What am I going to talk about? Well, I'm not going to talk about all that. That's crazy, okay? I have a very simple plan for the sequence of lectures that I'm going to present to you. And it's going to start out looking modest, and then I'm going to make it look even more modest. Then I'm going to make it look really dumb, and then I'm going to try to convince you that it's really the most important thing that we should be starting to look at, okay? So here's my plan. I'm essentially just going to talk about one stylized, simple version of learning. It's the one that you probably all already are aware of, which I call learning a function from data. You probably know as supervised learning, but I'm not going to emphasize that terminology too much. You just think of it as learning a function from data, right? So the abstraction is simple. We have some domain of objects X. That domain of objects could be an interesting domain of objects. It could be, the domain of videos or images or documents or sentences, something, right? And what we're trying to do is we're trying to learn some processing map, some processor that takes input objects and produces output objects. The output objects belong to some range Y. Those too could be interesting objects. They could be as simple as a number or a class label, but they could be quite a bit more interesting, like a parse tree or a parse of an image with annotations of objects, a parse of a video with annotations of events occurring in the video, and so on, okay? So let's try to think of this, generally as a rich, interesting problem rather than just a pale, plain problem, okay? So the game is quite simple. What we're going to do is take some finite set of training pairs. So what's crucial here is we get paired data, examples that show us what the input-output map is, but we only get finitely many of these. And based on this finite set of paired data, we go through our magical learning machine, and we'll produce a prediction rule or a function that relates inputs to outputs. Okay? And quite clearly, there is an extrapolation going on here. The idea is to take that small finite set of labels or output structures and extrapolate that relationship over the whole domain X, right? And in particular, what we're really hoping to achieve is accurate prediction on X's input objects that we haven't seen in our training set, okay? This can be trivial or impossible depending on how we set this up. And I'm not saying this is the most important current research problem in machine learning, but this is sort of the Drosophila of machine learning, right? This is sort of the basic problem that underlies a lot of the activity that's going on. And in fact, it's the basic kind of problem that underlies a lot of the application successes that are driving a lot of the interest in the field, okay? There are going to be variants of the problem, like what happens if you have missing labels on the output side or on the input side, and I'll get to those as time goes on. Okay, so let me just, I said I'd start slow, so let me just start slowly. How can we even do this on a computer? Well, quite clearly we have to face some pretty mundane issues, like, our input objects are going to have to be represented in a computer, our output structures are going to have to be represented, and maybe more challengingly, our functions themselves, the functional maps, have to be represented somehow as a program, okay? Say we conceive of ways to represent these input structures, output structures, and programs. The real challenge then starts, which is, okay, now we need some algorithm, right, that takes finite sets of paired data and produces some particular output program, right, some input-output map. Just to get started, I'm going to follow a very mundane, naive strategy. This strategy won't hold up for long, but it's the right way to get started, which is to approach this problem by deploying empirical error minimization. Now, empirical error minimization as a learning strategy makes two simple choices. It says all you have to do, if you want to learn one of these maps, is first fix some space of functions, some space of input-output maps that you're willing to consider. Fix that space, understand how to represent functions in that space. Once you've made that decision, the only other decision you have is to select a prediction error function. That is, if you have some true target output structure y, and then your learned map produces some guess y hat, we need to assess the prediction error between the guess and the target, okay? Once you've picked the class of functions and once you've picked the prediction error function, then empirical error minimization just reduces everything to a simple optimization problem. Now all we do is, given paired data, is we just have to solve this computational problem here, which is an optimization problem of computing the representation of some function little h in the class big H that just minimizes, say, the average prediction error on the data, okay? So just to make this brutally simplistic, let me just reduce it right down to the simplest thing that we all had to learn first, right? Learning a linear function from data. So let's look at learning linear functions. This is the simplest case where we're representing input objects just by a vector, some vector in Rn for finite n, okay? And then to be really dumb, let's assume that the output structure is just a single scalar number, okay? And we're going to restrict attention to maps between inputs and outputs that are just linear functions. Linear functions will be completely represented by a single weight vector, w, which is the same dimension as x, right? So we have some space x, we have vectors in that space, we have some vector w in that space. We take the inner product between w and x, and that defines a hyperplane, right, in the direction of w, and the length of w is the slope of the hyperplane, right? How exciting, okay? Now, next, so that's step one of empirical error minimization. We said, here's our representation of objects, and here's our class of functions, linear functions, okay? Next step is we have to choose some concrete way of computing the error between a guess and a target, okay? I'm going to propose that if I have some target scalar y, and I make a guess y hat, that I'm going to measure the prediction error between y and y hat by, well, kind of the obvious choice, right? The absolute difference between y and y hat. That just seems like the natural way to measure the difference between a guess and a target, okay? At this point, at least 3/4 of you are saying you should square that error. But that would be daft, okay? I'll come back to that later, okay? So let's just, let's not do that, all right? Let's just use the natural error prediction loss function that we would like to use here. Okay, and then Empirical error minimization then just reduces to this simple optimization problem, which is over the set of functions, which each is assigned a weight vector. So hence, over this set of weight vectors, we just solve this minimization, compute the minimum, the weight vector that minimizes the mean absolute prediction error. Okay? And then if we pull this off, we'll get some weight vector W hat, and that gives us a linear predictor. So question. Some of you will know this, but does everyone in this room know how to solve an optimization problem like this? In fact, if I said, exercise, go out and write me a program, 2 lines of MATLAB that computes minimum least absolute error predictors, is this obvious to you? I'm worried about people learning least squares and only least squares. Can you say, solve a linear system? But that's not going to work here, right? Okay. Well, so this, even though this was a natural choice, it does create a few technical difficulties for us. It turns out absolute error is not like a smooth differentiable function. It's a piecewise linear function. So the optimization problem we get is actually still an easy optimization. But if we think of it from a naive optimization perspective, we do encounter some challenges around the fact that it is not differentiable, right? We get this piecewise linear, happily convex objective, right? So if we want to solve this particular training problem, we're going to have to solve non-smooth optimization problems like this. In this case, actually, it's a trivial exercise. You could just code it as a linear program. In fact, just rule of thumb, if you have a piecewise linear objective and there's a finite number of pieces, you can pretty much always code it by assigning an auxiliary variable to each piece and just setting it up. Here, there's a trivial linear program. The way you could set this up as a linear program is for each training example, you just give it its own little error measure delta, okay? And then I'll just add these auxiliary variables delta to the minimization. So now I'm going to optimize over the weight vector and a vector of deltas, one for every training example. And all I'm doing is I'm setting up constraints that say that the predictions have to be within delta of the target. And then I'm just trying to minimize the sum of the errors, keeping the predictions within the errors. You think about it enough, you believe me that that actually solves the problem, okay? This is not a hard problem to solve. Now, I know, in signal processing or in 1920, this was thought to be a daunting thing, and we should avoid these kinds of linear programs and stick to just solving linear systems that you get for least squares. But that's crazy, right? This is in 1920. Computers can solve linear programs on millions of variables. You hit return, you get the answer, okay? If this is the natural kind of error measure you want to use, we should be empowered to use it. I'll say more about least squares in a bit. Okay, so just in our toy demo, we can now compute or learn from data linear functions that minimize the mean absolute prediction error pretty quickly. A couple lines of MATLAB, and then voila, right? So just to give you some demos, like if we have paired data where we get points with x values and y values, say 20 points. Sampled from this not quite linear looking function. We set up our linear program, we hit solve, it happily says victory, and that's what you get. Okay? Does that look like a good idea? All right. So here's the big question. Sure, we can model things and we can set up optimization problems and we hit, the big red button and we get solutions, okay? But that's not all we care about. Obviously, we care about is, how well is it going to work off the training data, right? And so the thing we always have to keep in mind is generalization. So that previous model, is it going to generalize? That is, if we sampled new data from the same distribution, are we expecting to get small absolute prediction errors? Or are we even expecting the prediction errors that we're seeing here to be at all representative of the prediction errors we're going to see if we actually deploy this in the real world, okay? Well, a couple of issues. One thing is the fact that we're minimizing a sum of errors summed over the data already is kind of tacitly making an assumption that the data is sort of like IID data. Each data point is being drawn independently from a fixed distribution. Because after all, if that distribution is changing and the data is changing over time, the idea of just kind of minimizing a sum of error, ignoring temporal order, and then using it to predict future data, that's not a good idea. Okay? So if you want to start dealing with non-stationarities or temporal structure, you have to think more carefully about even setting up the training problem than we have so far. Well, let's just make a simplifying assumption and say, okay, IID data. That is, we get a fair sample from a distribution, we fit that sample, and now we want to understand, are we making good predictions from new samples drawn from the same distribution? Well, then here we see the challenge, right? We have these two opposing forces. One is that the conditional distribution, the true conditional distribution, just might not be well modeled by any linear function, never mind the one that we picked. That would be bad, okay? That seems like the only issue, but it's not the only issue. So in a trivial toy demo like this, you won't see the other issue yet, but you're all aware of it. The opposing issue is that the empirical error might be way too optimistic. That is, we get a really wonderful fit to the training data, but it is not at all representative of the true test error that we're expecting on future data. And that would be a huge problem. So just to conclude this little sort of toy discussion, learning linear functions, is this even worth our attention or not? Well, it has some things going for it. Very compact representation of a function. I said, we have to represent these functions H as a program. What simpler program than just keeping a weight vector and computing an inner product? Okay, so it's compact and efficient. We get efficient training algorithms. In fact, you have to kind of be creative to get non-efficient training problems out of linear classifiers, okay, or linear predictors. And of course, once we've learned something, we get very efficient predictors. Okay, that's great, but it's got drawbacks. The obvious drawback is linear modeling is incredibly restrictive. So it appears, okay? And so this could never be really useful in any setting outside of a classroom, okay? You might think. By contrast, linear fitting might actually not be restrictive enough, we'll see shortly, and we are going to need to bring a lot more structure into the problem to prevent just even simple linear function fitting from going off the rails, okay? So it would appear that, as a standard starting problem, linear prediction from labeled input-output pairs may not be worth much. And yet, here's what I'm proposing to do in the sequence of lectures that I have. I'm actually proposing to do only linear function learning, okay? This isn't going to be like, analyzing significance bars around regression coefficients, if that's where you think this is going. Here's something that astonished me. And I think this should astonish you, and I'm going to try to convince you over the next couple of lectures that it is astonishing, that if you look at current efficient tractable approaches to machine learning, and I'm not saying linear function prediction, look at any application area, vision, language, document processing, what have you, and you look at the techniques that are actually reliable, used by people who aren't research experts, or even used by researchers who aren't optimization experts, under the hood, if you look deep enough, they're almost all linear modeling approaches. In fact, linear modeling is the dominant technology for efficient, flexible, supervised learning techniques that are out there. And I'm not saying I like this. I'm not saying this should be true. I'm just the messenger. I'm going to show you that this is largely true. How could this possibly be true? Well, the problem is right now, most of you are just thinking like, ooh, linear functions, like I draw a line. Okay, well, fair enough, but you're missing something. And here's what you're missing. Of course, it's really easy to generalize this simple setting, right? And in fact, we can split these generalizations into a few easy separate steps. Step one, all you got to do if you want to make things nonlinear is take that input representation you started with and expand it. Right? Generalize that input representation so that suddenly the predictor you have now is some crazy harebrained nonlinear function of the data you started with. Okay? That's easy, and in fact, it's really easy to train what look like nonlinear predictors just by a simple trick of expanding out the input representation. Okay? So it's not even deep, right? And in fact, most of the work there is spent not dreaming up new ways to expand feature representations. That's kind of easy. It's how to control the capacity of what you've created to prevent it from overfitting everything like mad. Okay? So one reason why linear modeling is powerful is that we can generalize the inputs. Well, here's the other extension, which makes it very powerful. In fact, this is the reason why it's really predominantly applied, is that it turns out, of course, it's also almost equally easy to generalize the outputs. That is to impose a nonlinear transfer between the linear predictor and the ultimate output prediction. And in fact, not only can you impose a nonlinearity there, you can impose multivariate outputs, and you can impose structure on the multivariate outputs. So in fact, you can think of something like taking a sentence, which is a sequence, it's not a vector, and yet learning a map from a sentence, a sequence, say, to a parse tree, simply by re-expressing the sentence as feature vectors, learning some linear model, and then expressing the output structures through some multivariate extension with a structure constraint. Okay, this is all high-level mumbo jumbo. Within 2 lectures, we'll all be seeing how easy this all is. Okay, and if you know it already, well, you're at an introductory course. I don't know what to say. Okay, a final. So it turns out those are pretty easy. So if you take a linear map and then I generalize the inputs and I generalize the outputs and make them both nonlinear, you're not going to be too surprised to discover that there's a lot of power there. Okay, and what's particularly effective about this is that even with these 2 generalizations, they operate completely orthogonally to each other. Anything I do on the input side doesn't interfere with what I do on the output side and vice versa. They're all efficient for the most part, unless you really do something crazy. So you have this very flexible tool that can model very complex input-output relationships between very complex objects, and you get efficient training algorithms, a lot of flexibility in choosing outputs and output losses and input representations. This really is the core technology that's driving a lot of these application successes of machine learning currently. Okay? There's the kind of the cooler thing, of course, is like, ooh, nonlinear. Even though we've got a lot of nonlinearity, there's still going to be things we'd like to be able to do that we can't. The third topic I'm hoping to get to is to extend this framework one step further, which is to introduce latent variables. So between a nonlinear transfer, linear map, output transfer, maybe interposed in there somewhere, we might still postulate the existence of some latent structures. Okay? Once you're doing that, you've pretty much covered almost all thinking I'm aware of in any sort of function learning process. Okay? What we're going to discover is that we can generalize the inputs and outputs without sacrificing tractability whatsoever. The moment we start incorporating latent structure, we're in a world of difficulty. It's a lot of open research. There are very few things we can do efficiently right now, but you know what? Progress is being made as we speak. And in fact, in the last few years, even in the last few years, there have been some really nice extensions where you can exactly solve for certain types of latent structures in the middle of a generalized linear modeling framework and get tractable, effective algorithms. And I'm going to at least try to talk to you near the end of my sequence about, say, a current research project that we have underway there. Okay, worst case, if you're going to, take an introductory course in machine learning, you need to learn about generalized linear modeling for no other reason than at least this is the quickest way to get up to speed on a lot of what's going on. Okay, a lot of the technologies that are really having an impact. And it's also the quickest way to really empower you to do interesting things quickly. Right? You don't have to first study functional analysis for a year to do this. It's trivial. You don't have to even first study probability and measure theory for a year to do this. It's all basically an exercise in straightforward linear algebra and calculus, and you get empowered right away, and you can go off and do things. And if you want to, deploy sort of deeper, richer areas of mathematics to what you're doing, you're welcome to do it, but it's not a prerequisite. Okay? Oh yeah, so here's sort of the sequence that I had planned out. You're going to find the sequence annoying, but anyway, but it's conceptually clean. So the sequence I have planned out is step 1, generalize the inputs. So I'm going to start with linear maps, really dumb linear maps. I'm going to do nothing to the output, so it's still going to look really dumb, like we're just predicting a scalar number, right? And I'm going to spend a lot of time just sort of explaining the various issues and techniques and understandings that people have come up with to generalize the domain representation. The whole while you'll be unimpressed because we're just predicting a scalar. However, this is a clean way to do this. Once I've gone through that, then I'm going to come back and generalize the output. I'm going to go from scalar to multivariate to nonlinear to structure. Okay? And it'll be totally factored. That is, anything that we do here and anything that we do there are mutually compatible. They have nothing to do with each other. They don't interfere in any way. Okay? So if you find the rest of today's lecture getting really dry, it's probably because you don't like predicting a scalar. And I have to convince you that that's not really what's going on. Okay? And then part 3, latent structure. So themes running through this is, trying to respect what I started out saying is that learning doesn't happen for free. There is no universal learning. It's a game, it's a dance between the available data and the prior knowledge and structure you're imposing on that data, right? And success is due to some combination of these two factors. If I have massive amounts of data, like all the data, if I'm at Google, maybe I don't need so much prior knowledge. I can let the data itself do a lot of the setting for me. But even at that scale, models can grow at a much richer, a much more rapid scale than data. Okay, so we need to understand how we can model things flexibly, for sure. All right, but at the same time, we need to be doing that while respecting these other issues. One is we need to be able to, well, ideally, retain computational efficiency, both in training and prediction, all the while understanding generalization. That is, how can we not over-model the data? How do we prevent ourselves from just fitting noise and producing models with no predictive value whatsoever? So I'm not going to sort of talk about any of these as separate topics. I'm just going to try to remind you of the intuitive issues as they arise. Okay. Oh. Sorry. So that's the end of my lecture 1. I can't quite see the clock. So what are we at? 9:05? Okay. 1 minute break. Stretch your fingers. I don't know. Let me just...